researcher. She works with the New Star and UVEX team on X-ray spectroscopy, photoionization modeling, and low mass galaxy frontier. Before moving to California, she completed her PhD in galaxy evolution at the University of Cambridge. Her research sits at the intersection of astrophysical plasmas, radiative processes, and numerical methods, with an increasing emphasis on machine learning approaches, including surrogate models for high-resolution spectra. She will soon be joining Los Alamos National Laboratory as a Feynman Fellow, where she plans to apply similar techniques to work on different problems relating to inertial confinement fusion. So please let me join me in welcoming Asha.
Thank you all very much. It's an absolute pleasure to be here. You are a wonderful department and a great IT team. This was the most seamless experience I've ever had, so kudos to everybody. And today I'd like to tell you something about how supermassive black holes grow, or at least what we can do to understand their growth over cosmic time. And hopefully, I can motivate you to care about this problem for two main reasons. First of all, I think by now we have established that AGN feedback is the primary reason why galaxies stop forming stars in the universe, and that's what I've been mostly interested in during my PhD, where we've shown that supermassive black hole mass is the key ingredient that you need to look out for when you're determining whether a galaxy is star forming or quenched, and it's true for simulations as well as observations. And since then, we've extended it up to redshift 2, redshift 4, and in different galaxy categories, showing that this is a uniform prediction of all models and then verified in observations. So long as you are a massive enough galaxy, your black hole really matters. So all of this work, of course, relies on the idea that the total output of energy output of an AGN is related to how much it grew. And what this translates into in simple equations is effectively the total energy output is some effective coefficient eta, which we of course have to decompose into radiative efficiency and coupling efficiency, but let's gloss over that detail. Most importantly, it's simply the total integral of your accretion rate as a function of time, i.e. black hole growth as a function black hole growth via accretion, that ultimately determines the historical output from an AGN. And of course, on the black hole growth side, we also would like to know how much mass has been lost or has been gained in black holes through mergers, how much of that energy has to be removed from your equation. So I would argue that in order to understand AGN feedback fully, we need to understand how black holes grow as a function of time. There's no other way around this. There's another good reason why we should care about their growth, and it is the fact that we simply don't know where they came from. Ultimately, we have two main competing theories for how supermassive black holes originate at high redshift. One of them being the light seed scenario, where you start with population-free remnants that go through your regular star, explodes into black hole scenario, which then progressively merge, accrete, and become big very, very quickly. These are low mass seeds. Of course, there's the competing scenario of heavy seeds, direct collapse of very large molecular clouds that initially give you those supermassive black holes between 10 to the 3 and 10 to the 5 solar masses. Now, these two competing theories are attractive because, as we've seen from recent JWST results, we have no idea which one is right. To be more precise, some of the highest redshift supermassive black holes, we're looking at black hole mass on the y-axis and redshift on the x-axis. Some of the most massive supermassive black holes as early as redshift 11 or redshift 10, their masses can be explained by any combination of competing theories, be it light seeds, direct collapse, and especially if you look at the figure on the left-hand side, you can see that your 10 to the 6 redshift 11 GNZ 11 galaxy supermassive black hole lies firmly within direct collapse, Eddington or super Eddington accretion, depending on what you choose your redshift of origin to be. So I would argue that we need to know how black holes grow, not only because they're important for galaxies, but also simply because we don't know where they came from. And ultimately, you can play this game of learning how they grow as a function of cosmic time in two ways. Either you do population-based studies, the idea being you trace your black hole populations across cosmic time, you measure their masses, compile samples, and see how the populations evolve. This is something that hopefully new Athena will help us do in complement with results from gravitational waves delivered by LISA. Or you can play the game the other way around. You will look at low redshift diagnostics, and that's exactly where the talk today lies. So you can imagine some supermassive black holes growing here cartoonishly via accretion. They will lead to some form of final measurable low redshift outcome. And you can also imagine black holes that grew through different paths, here illustrated by squibbled mergers, that will also give you a slightly different value of a diagnostic you're interested in at present day. And that's precisely where spin lies. Because black holes ultimately are very simple astrophysical objects. They basically have two parameters. Mass cannot tell you how mass grew as a function of time. Bad odds of tracing it back. And angular momentum. And that's precisely what the talk is about today. Supermassive black hole angular momentum measurements. I will refer to as the dimensionless spin parameter, ranging for us between 0 and 1 for the rest of the talk. So throughout this long introduction, all I wanted to sketch out is that if you want to get at how supermassive black holes grow, you either do it as a function of time or you do it at low redshift. And if at low redshift, probably angular momentum measurements are the way to go. Now, why would that be the case? If you think about a supermassive black hole accreting through an ordered accretion disk, every single lump of matter that comes with an already aligned angular momentum simply increases the magnitude of the angular momentum vector of your black hole. If you've got chaotic accretion, so you're coming from all different sides, all the random orientations of your matter packet angular momenta on average will tend to spin a black hole down. And if you've been doing gravitational wave science for a while, you will also know that depending on the initial configuration of the input spins of a merger, a black hole, be it supermassive or stellar mass, can end up with a range of output angular momenta, depending on what's the initial orientation of your merger. So that's how in principle angular momentum at present time connects to the growth history of your supermassive black hole, and it has been shown to work incredibly well in semi-analytic models. Here I'm showing you a nice visual from work back in 2014, where you can see that galaxies which are spirals, implication being mostly ordered accretion, seem to have spin values, that's the y-axis, concentrated close to 1 for black holes across all masses between 10 to the 6 and 10 to the 9. However, for ellipticals that have undergone violent relaxation post-mergers, they on average have massive supermassive black holes that tend to have much lower spin values. And there is a whole body of theoretical work in semi-analytic models that more or less paints a similar picture. Details differ. What is really exciting to me is that as of recently, the discussion of spin parameter evolution entered cosmological simulation scenario. And for those of us who don't work with cosmological simulations, let me remind us what they do. There are a couple things they model explicitly, like collisionless dark matter dynamics, magnetohydrodynamics on a grid, or in particles, depending on your flavor of numerical method. And all of that is, of course, done in Newtonian gravity. Now, one thing to note on this slide, the resolution of these models that are cosmologically representative is roughly 1 comoving kiloparsec, which means that there is a ton of physics that we simply cannot capture directly because we don't have the resolution. And that includes processes like star formation, gas cooling, chemical enrichment, and most importantly for our discussion, formation and evolution of supermassive black holes. So within that context, we are currently at the point where modern models are introducing supermassive black hole spin evolution and spin coupled feedback. And just to name a few, I wanted to highlight recent models and collaborations like the New Horizon, Coliber, if I'm pronouncing it right, or some work within Open Gadget 3. These are already existing cosmological simulations with real predictions for low redshift measurements. And there's active development on the models themselves, like the Obsidian model that is based off of, that is coupled to the SIMBA cosmological simulation or the galaxy formation model, or the recent unified model published by Sophie Kudmani that was based on AREPO, for those of you familiar with those codes. So there's plenty work being done in this space, and within that, I would like to highlight this excellent paper published jointly by Ricarda Beckman and Rebecca Smethurst over in the UK, where they've taken the results of the Horizon AGN cosmological simulation and asked a very simple question. What is the low redshift distribution of spin parameter measurement between 0 and 1, but here axis is cut off, for black holes that grew via accretion only and those that grew via accretion and mergers? And we don't need to do any fancy statistics to see that purple is statistically significantly different from gray at a level of 5 sigma for this particular comparison. So this figure alone, if we trust the Horizon AGN cosmological model, should tell you that in principle, if you were to go away and measure spin parameters at redshift 0 for your supermassive black hole sample, in principle, you should be able to tell whether their growth histories are dominated by accretion or accretion mergers. So that's the premise we're working with here. Now, how do we get to measure this? And that's my favorite part, because it's ridden with difficulty and challenge. So for the purpose of measuring supermassive black hole spin with X-rays, we assume there is a black hole or a compact object surrounded by a geometrically thin and optically thick accretion disk. Now, above and below said compact object, there is a cloud of non-thermal electrons we refer to as corona. Now, what exactly that corona is, ask your favorite GRMHD theorist. As many theorists, as many answers. But if we can hopefully agree that this is some form of a persistent population of non-thermal electrons, be it a base of a jet or an outflowing sandwich disk wind, these electrons have the capability of taking thermal photons from the disk, upscattering them to very high energies and generating your X-ray continuum. Now, part of that X-ray continuum, the power law that we see from AGN, will then re-radiate the disk back, get reprocessed or reflected, and sent to the observer, as shown in the schematic. What is absolutely critical about this is that the exact form of that reprocessed signal will strongly depend on where within the gravitational potential well of your supermassive black hole you are. The closer you are to the ISCO, the more gravitational reddening your photons will experience, and hence your expected reflection signal will be modified. How it illustrates itself in practice for, say, a Schwarzschild-like black hole, so non-rotating, you will see the most important signature in a reflected spectrum. That's the iron K alpha line, which is a fluorescent line, the most powerful signal we get out of reprocessed emission, and a Compton hump. So this one looks pretty narrow. The black hole is non-rotating. Your ISCO is firmly within a Schwarzschild ISCO should be. Now, if you go to maximally spinning black holes and your ISCO shrinks or gets closer to the event horizon, suddenly the gravitational reddening I was talking about takes place. And the name of the game in measuring spin parameter is effectively doing template comparisons between A and B on a spectrum. So you take your favorite X-ray measurement and you compare template spectra, trying to figure out which one is the best fit. And the shape of your iron line mostly is the primary constraint for where the ISCO is. And as general relativity tells us, the location of the ISCO uniquely defines the angular momentum value, or let me rephrase that, vice versa. So one thing I did not appreciate when joining the field is that there has been a debate on whether or not this is real at all, whether relativistic broadening is a genuine measurement, because it started all the way back with the first observation back in 1995, where the clear broad iron line was observed in this telephone number of MCG 63015, which apparently is one of the best studied AGN out there. And the reason for confusion was, you get a broad line, but maybe it's just apparent broadening causing that by preferential absorption on one side of the line. The other camp, of course, said no. These are relativistic effects, and this is nothing to do with absorption. And then NewStar came, launched in 2012, and clearly showed that one of those theories is statistically significantly discarded. And I think this is a beautiful story of why we should be building new missions, why we should be investing in exploring the universe, because had it not been NewStar, we would be still debating this point until present day. So as of today, of course, there has been a whole industry developed around spin parameter measurements and reflection spectroscopy, as we call this field right now, where not only do we carefully model all the atomic physics and interaction of light and matter within the disks themselves. So these are local reflection models. Here I'm highlighting one of the papers by Javier Garcia. And of course, there's a whole industry of doing the relativistic post-processing and ray tracing in realistic accretion disks. Here coming from Thomas Dowser's personal website. Now, before I go on to arguably the most interesting part of the talk, I wanted to highlight a couple of caveats that not everybody appreciates about spin parameter measurements or X-ray reflection spectroscopy. Number one, disk thickness. And what I mean by this is in all of our measurements, we assume that disks are infinitely thin. They're basically razor thin flat tables. But in practice, we know that with we expect from our theoretical knowledge and GRMHZ simulations that disks will not be thin and flat. Now, what happens if you account for this, even in a Shakura-Sunyaev type solution? Blue corresponds to the thickest disk here, black corresponds to no thickness in this plot. What really happens is you've got parts of the disk being obscured, self-shadowing, that reduces your bluing of the line. You've got eyeball illumination that preferentially boosts your red signature, and this altogether results in a net bias, inferring spin a little bit too high. And you can see that, especially here, where your iron line that used to be rather narrow, with all of these effects combined in a real thick disk solution, suddenly becomes much broader and looks like a higher spin solution than it really should be. And I would strongly encourage you to look out for updates on this research led by wonderful undergraduate students, both at Caltech and Wake Forest University, who are currently working on precisely characterizing the degree of bias you can incur by simply assuming a razor-thin disk alone. Caveat number two, plunging region emission. For everything I've told you so far, we just assume the disk extends all the way to the ISCO and there's nothing else, or not enough density. But as we know from GRMHZ simulations, there is enough matter density. ISCO is in no way special if we put enough magnetic fields in. So what happens if we have matter within your ISCO? Where the answer is your lines broaden. And what that means is that all of our previous templates that assume no emission from the ISCO are simply inferring spins too high by artificially deflecting your lines to meet the broadening. And again, a quick advertisement for papers coming later this year from Gulick, Mastroserio, and Javier Garcia on that topic. Finally, table model interpolation, and that's where my recent interest lies, and a lot of rabbit holes have been gone down in, because a big part of these calculations relies on photoionization, interaction of light and matter, and this problem is not easy. These are inherently computationally expensive calculations, and if you want to span your parameter space, you have to perform these computations over and over again. Since they are expensive, the way people usually go about this is they pre-compute them on some form of HPC system and put them in a table. Now, if your table is too sparse, when you interpolate over said table, it can lead to catastrophic uncertainties or errors introduced by interpolation alone. And here I'm showing you results from a photoionization code X star. Some of you might be familiar with. Long story short, if your tables are sparse enough, it will lead to very large errors. And one way we can try to address this is building surrogate models. This figure is a little bit outdated, hence doesn't look as impressive as I would like it to. However, the main message is here. Hopefully machine learning can help us not only decrease the uncertainties if we focus on the bottom panel, but most importantly in compressing the representation of those gigantic tables that otherwise at high X-ray resolution would be computationally unfeasible for real fitting. Okay, so now that I've told you about all the dirty caveats, let me present to you the state of the art we currently have. And that is impressive, an impressive set of circa 50 measurements in the spin parameter y-axis, black hole mass x-axis for supermassive black holes. And I want you to notice a couple things. First, bulk of these measurements are only lower limits, which in principle means they have no meaningful error constraint. The ones that do come with very generous error bars, and it's not the property of the data. It's not the property. It's not that the data is not good enough. We're already pouring more than enough megaseconds into this picture. The physics of this problem is simply hard. We need better instruments. So if we ask how better these instruments have to be, you know, coming back to work done by Rebecca and Ricarda, if you extend that one-dimensional image into 2D to match the space I've just shown you before, your black holes that grew via accretion, these are the blue population up there, those that grew via accretion are the orange, then you account for the most significant bias between radiative efficiency and spin parameter. Highly spinning black holes are simply more luminous, they shrink together. And if you overplot the current state of the art measurements, well, you can clearly see that they're not very constraining, and you can play all the games you want here. This is a simple binning in a supermassive black hole mass. All you can get as of today are at best lower limits, and that's where opportunity for future X-ray missions lie. And to be more precise, how good we can expect this picture to be in a decade from now on, together with Julia Sislenis and Peter Borman, we're writing a paper for the New Athena special issue later this year that will precisely answer the question of what New Athena can do for this picture. And as a final note, I should also say that spin parameter measurements are not only important for our understanding of supermassive black holes, but also for the cosmological models themselves. Because right now, when we calibrate all of those extensive subgrid models that I listed before, we have to use some forms of observables. Usually, these are galaxy scaling relations. For black holes, we mostly have the M sigma. If we can get precise enough measurements of spin parameter, this becomes an orthogonal axis for calibration of our subgrid models. And I know we're looking far away in the future, and theory is way ahead of observation, but my hope for the field is for supermassive black hole angular momenta to be yet another calibrator of cosmological models. So to conclude, hopefully we can all agree that supermassive black holes are absolutely critical for galaxy evolution, and their growth history is one of the most important quantities we can constrain in order to understand said impact. Supermassive black hole spin or angular momentum retains a memory of accretion history, hence it can be used as a useful probe. Current cosmological models are showing promise in discriminating power of spin parameter measurements at low redshift for understanding real black hole populations, and hopefully next generation observatories, including New Athena, combined with more sophisticated analysis methods, will turn spin into a real quantitative cosmological probe. Thank you.
Thank you so much, Asha, for the lovely talk. Any questions?
Thank you, Asha. As I told you, I did even know. Thank you. So you mentioned a number of caveats about the measurement of the broadening of the iron line. I was wondering if there are also instrumental effects that need to be considered. For example, nonlinear effects, phyla, etc., and things that could also potentially distort the specific shape of the line, and whether those are more or less relevant than all the other caveats that you mentioned. Thanks.
So to answer from the back, On average, they are less relevant than all the other ones that I've mentioned before, because systematic uncertainty in the models exceeds anything we can add instrumentally as of now. I should also say that these biases are not characterized very well. There's a reason why people are currently working on this. Number two, with the launch of CRISM, we all got excited about teasing out the exact shape of the iron line, and it turns out that our models are just not cutting it. So right now we have to play the theory catch-up game of explaining some of the more complex iron line shapes, which are not only caused due to broadening, but they are a complex interplay of broadening and absorption, and that's where the problem gets really, really steep when you try to model really complex physics at this high resolution. As anything in real observable universe, so long as your resolution is poor, every model fits. Suddenly CRISM comes along and you start having problems. Yeah.
Thanks.
So thanks for the talk, and I want to ask a question about the model interpolation.
Yeah.
I think it's terrifying to a person like me. But so I guess my question is, since X star is one, then there are many other table models. If we want to start looking at some of the rest of those, what are the features we should be worried about the most? Like, is it photoionization where you start to see things get screwed up? Is it other effects, or should we just be assuming that it's just a bare mathematical problem and that it's just the fact that the interpolation is not good?
Great question. So for the purpose of measuring spin, all of this, once it has gone through all the ray tracing within a real disk and gravitational broadening, this becomes negligible. So if you're interested in spin, worry less. If you're interested in the exact physical properties of your wind, of your chemistry, where you're in trouble. And you really, really are. And it's not only because the table models people are playing fast and loose with table models by designing their own sampling points, but also because photoionization is inherently hard, and some of the most interesting physics lies in the range of the parameter space where your solutions are multi-valued. You've got thermally unstable solutions, and depending on which algorithm you choose, it might either settle into the hot or the cold branch, and it's all down to numerics and instability. So if I were to make a recommendation, is if you're after chemistry and if you're after the ionization profile of the plasma you're interested in, never do it with a single code. Always do it with a set of different numerical methods, and for the love of everything that's holy in science, check for your convergence, because these models struggle with convergence.
Okay, thanks.
Great talk. A lot of interesting stuff. I wanted to ask about, it looks like it'll be hard to make enough and precise enough measurements to really distinguish between models of accretion. Would it be helpful to include some other parameter in correlations, like looking at what kind of galaxy it is? Whether it's an elliptical or a spiral or anything else that I may not be thinking of that would help that.
So excellent question. Let me answer to that twofold. One, what I didn't show in the slides, because unfortunately the mission didn't get selected, the high energy X-ray probe would be the perfect instrument to go after enough measurements at high enough precision, because it's effectively high energy coverage of new star and the energy coverage of XMM all in one simultaneous instrument. And over 5-year mission lifetime, it would have given us tight constraints that even in those coarse bins are statistically differentiable at a level of 4.5 sigma. So it is possible. The instruments that we currently have planned, a no-go. So now to answer the question you genuinely asked, the answer is there is hope, because there are already studies like this. So especially cosmology simulation experts, and they do not only focus on the black hole properties alone, but they also fold in, as you said, galaxy type, galaxy color. And when you start introducing those extra parameters, then hopefully, and you hope that your problem is posed well enough, then your big hierarchical Bayesian model hopefully settles on something that is useful to you. Now, what exactly we settle on? That's exactly what we'll be working on with Julian today.
One more question, but just to advertise that Asha has made the current sample of supermassive black holes with X-ray reflection for spins available on GitHub. And we have listed some additional quantities of interest. So the intention is that as we get more measurements or as people are aware of more variables, we should be able to update that.
Well, thank you for a very excellent talk. Curious about two effects that you didn't discuss. One is the change in spin when the spin is converted to external energy in jets.
Yes.
The other is, I think your shapes of the reflected iron line do depend on a continuum measurement. So the effect you didn't discuss is of the continuum X-rays that are not coming from the disk. And that's speculative, but there may be parsec scale jets, there may be knots like an M87, there may be mass outflows like people here are finding. So
Excellent, two questions. And to answer the first one on the jet spin down, if I come back to the slide about all the different models in cosmological simulations, because I think it's important to appreciate all the hard work that has gone into them. Depending on the flavor of the model, some of them will have jet spin down already treated. So for example, Sophie Kudmani's model and the Obsidian model, they are not run in full-blown cosmological simulations yet, but they both include jet-induced spin down. So their final spin parameter values at redshift 0 will have had that effect already accounted for. This is not true for New Horizon, or I believe it is true for Oliver, and I'm not sure about Volcanic Gadget 3. So the effect of jet spin down is very similar to the effect of merger-induced spin reduction or chaotic accretion post-merger, effectively shifting your black holes down. Now, disentangling between jet spin down and chaotic accretion might be a more difficult task because cosmological models or implementations do not agree there very well. Or let me rephrase that. The signatures in the spin mass plane predicted by these two competing scenarios are just very similar. So that unfortunately remains a source of uncertainty. As for illumination from an external source, if the jets are extended enough, I would imagine that this would be a negligible enough effect that may not lead to significant biases. But I say that only on the cusp right now. I'm not aware of the top of my head of the studies that study this bias in detail. So I am very happy to prove it wrong.
Okay. Yeah. Well, unfortunately, we have to move on to the next talk. But if you have more questions, Asha's timetable has been shared. So let's thank Asha again for listening.
So how do I just maybe slideshow? What is this? Live this, and then wait, I have to share the screen. Wait. Sorry, I just. Here? I think you have to full dust. Oh no, stop. No, that's wrong. Sorry, I'm so sorry. This is clearly not what I wanted. That's what I wanted. I tried. You have to do full desktop. Full desktop. Yeah. Oh, okay. Is that what we're doing? Yes, perfect. Great. This is your clicker. Thank you. And I'll turn that off. Or do you want to be met this way? Sorry. Well, this one first. I send here.
Okay. Thank you for your patience with the technology. But next we'll have Hannah Gulick, who is currently a PhD candidate in astrophysics and an NSF research fellow at the University of California, Berkeley. Her research focuses on time domain astrophysics and the development of space-based optical and gamma ray instrumentation. So last week at the ITC luncheon, she already gave a really good summary about Curious CubeSats constellation. And she also works on the BTO instrumentation on NASA-funded COSMOS mission. Today she'll be talking about uncovering compact object population with these space-based surveys. But in the fall of this year, Hannah will be starting at Caltech as a NASA Einstein Fellow, where she will continue developing new survey strategies for the dynamic universe.
There you go. Thank you. Can you hear through this mic okay? Okay, perfect. So yes, my name is Hannah Gulick. I'm a PhD candidate in final year at UC Berkeley right now, and I work with Professor Jessica Liu and Dr. John Tomczyk on 2 different space-based all-sky missions. So I'll be telling you a little bit about each of these and hopefully getting you excited for them and explaining how we can use them to uncover populations of compact objects. So if you're at my ITC seminar last week, you'll get a little bit of repetition, but a little bit more summary too on what Curious is going to be capable of doing. So to start off, there's a huge scientific frontier right now associated with compact objects, specifically black holes and neutron stars. For instance, some of the big questions we have are, is there a mass gap between the lightest black hole in the universe and the heaviest neutron star? How do these systems evolve? Are they in binaries? Are they isolated? And then specifically, how do they get into these systems that merge to produce gravitational waves? In addition, we don't understand their general populations very well. And to really emphasize this, we have simulations that show that there are billions of stellar mass black holes in the Milky Way alone, and we have observations of only a dozen of these in binary systems in a single isolated event so far. So in order to understand these bigger questions, where we really need to start is with the demographics of compact objects, and we can do this just by observing them. However, this is kind of complicated to do, so this is what I've been focusing on for the past 6 years. So this plot here shows you a bunch of different science cases that are associated with compact objects, and I'm going to split it into 2 regimes, and I'm going to shift it a little bit from what I talked about during the TC seminar. So in this upper regime, the higher energy or the longer time scale regime, we have signatures from existing compact objects. So these isolated remnants that produce microlensing events. And the best way to observe these is through the optical by looking for microlensing signatures. At the shorter time scales, we have really explosive fast events associated with the birth of compact objects. And you can observe these in many different wavelengths, but if you really want to capture what's happening at the moment that these events are merging and creating a compact object or a star is dying, the best thing to do is look through the high energy. And so down here, I've got a gamma ray focus. And it turns out to look at the full life cycle of compact events, you really need multiple wavelengths. So through my PhD, I've approached this through the gamma ray and the optical through 2 different missions. And I'm going to start with this longer time scale first by looking into the optical. And so when we're looking at these long time scales, we can study demographics by looking at specifically these isolated events through microlensing signatures. And what happens when you have a microlensing signature, I'm showing you an animation over on the right over here, you have some kind of compact object, it can be a star as well, that passes in front of a background source. And when it passes in front of this background source, the object's gravity causes more light from that background source to be lensed towards your telescope. So what you end up seeing is a magnification over time. And you get 2 interesting things from this magnification plot. First is TE, or the time that your event takes to cross. And the second is pi e, and pi e is your microlensing parallax. And you measure this from the asymmetry of this downward going slope of the amplification, and it arises from parallax caused by you moving around the Earth while you're observing the event on the sky. And what happens when you plot these 2 against each other is something kind of magical. Not really though, it's just physics. Your black holes separate themselves out into this lower right-hand corner. And this is because they're more massive, so they have longer time scales, and they have smaller microlensing parallaxes. So yeah, black dots here are showing you black holes, and then we also have some microlensing showing stars, white dwarfs, and neutron stars. So in theory, if you can get small enough error bars on pi e and TE, you can confidently say that you've detected a black hole microlensing event. That's not the case right now, though. So this is showing you some microlensing events from OGLE, which is one of the leading microlensing surveys on the ground right now. And the main takeaway from this plot is that the error bars, specifically on pi e, are too big to confidently identify which of these candidates could be black hole events. And so typically what you do when you have a microlensing event, this is photometric microlensing, then you report it and you do astrometric follow-up, and through astrometric follow-up you can measure the Einstein radius around your event, which gives you directly what the mass of the lensing object is. And it's kind of expensive to do astrometric follow-up. So From this plot, you wouldn't be able to confidently say any of these points were worth following up with astrometry. Therefore, we don't have a lot of measurements of black hole events right now. However, we can build an instrument that's capable of doing confident photometric microlensing. And to do this, we need something that's long duration to be able to capture long duration events from specifically stellar mass black hole microlensing. We need regular cadence so we can really sample consistently along this light curve and detect any weird behavior in the upgoing or downgoing slopes that show us that we actually have binary systems instead of single lens and single source. We need really good photometric precision, so we have small error bars on this light curve, and then we need great spatial resolution and a moderate field of view so we can detect a lot of these events. So our solution to this is Curious. Curious is a concept for an all sky, all the time telescope, which is built from 300 or some number of CubeSat telescopes. And so I'll show you here what the Curious CubeSat looks like. So we based the design around a 16U CubeSat, which is just 20 by 20 by 40 centimeters in size, so they're pretty small. And then we'll have a 15 centimeter aperture on the inside. And these first CubeSats that we're thinking about building will be in the optical bandpass. We're hoping to integrate IR at some point, but we're a bit detector technology limited at this point, specifically in cost. And then our field of view will be around 35 degrees squared. The minimum lifetime is going to be 2 years, but we've made sure that all of the electronics are rated up to 5 years on orbit. We really want to push for this 5 years because it takes time to launch a bunch of CubeSats into space, so you want to make sure that your first CubeSats are still alive when your next set of CubeSats get up. Our sensitivity is down to 21.7 in the R band. This is in a 15-minute stacked integration for an SNR of 10. And then our cadence will take individual 30-second exposures and then stack these on board up to 15 minutes. And we can see any target on the sky for 10 months out of the year. And this is due to our solar keep out angle. And then we're looking at a low Earth sun sync orbit for these satellites. This plot here emphasizes the power of Curious compared to existing surveys that we already have. It's a bit dense, so I'll go through each of these individually. Up in the upper left, I'm showing you the instantaneous area for the telescope versus the limiting magnitude per visit for each of these telescopes. And then these two blue points are showing you some space-based surveys that we have, so Gaia and TESS. And then the gray points are showing you some of our leading ground-based surveys like Rubens, ETF, and Atlas. This point here is showing you Curious initial demo, which is just 3 Curious CubeSats. And then this one is showing you what it would be for 300 Curious CubeSats. And so what you find is that we have a competing limiting magnitude with our some of the leading ground-based observatories, and we're beating what is currently in space. And then our instantaneous area, especially for the full constellation, is unmatched by anything currently in existence. Over here, I'm showing you what our solar keep out angle looks like. So this is one of the main advantages for going to space. You can observe closer to the sun. So you can see more of the sky at any time throughout the year, which means that you can observe your targets for longer. And then down here, I'm showing you just some of those interesting events that we were talking about earlier versus what Curious timescale would look like. So we cover a lot of these different timescales. In terms of science, I'll show you one of the Curious science cases. This is going back to the stellar mass black hole microlensing. I showed you this plot earlier. This is real observed data from OGLE. And then over here, I'm showing you some simulations that we ran using Popsicle, which is a compact objects demographic simulator. And this is what we would expect to get with Curious ID, which is the first 3 Curious CubeSats, so a cadence of about 30 minutes. And you can see down here that our error bars are small enough that we're able to pretty confidently identify black holes even without astrometric microlensing. So we could confidently say that some of these are black hole candidates, should probably still follow them up with astrometry, but through this, we'd be able to detect about 50 black holes per year per Curious field of view on the galactic center. I'll emphasize again that we've only detected 1 to date, so this would be pretty revolutionary for stellar mass black hole demographics. And with these numbers, we'd be able to constrain the fraction of stellar mass black holes in the Milky Way galaxy to about 10%. Perfect. Okay, so anytime I talk about Curious, and I didn't do this in the ITC, so I wanted to make sure I brought it up today. Something I think is super important now that we're entering this domain of space-based constellations is talking about how we can make them sustainably. And so Curious, a lot of my work on Curious has been focusing on how we can do this sustainably in a way that doesn't impact ground-based observing, it doesn't impact humans right to the sky, and also doesn't give us a big heap of debris up in space once we launch them. So one of Curious's main advantages is that it's very small. We've chosen a 16U CubeSat instead of some of these small sets that people are moving towards because they reflect less light and because they're less likely to get hit once they're on orbit. We've also added propulsion into each of these CubeSats so they can do active avoidance, so we don't hit anything on orbit, and we can also actively decay from our orbit once the end of the mission's lifetime has been reached. In addition to this, we've looked a lot into what people are starting to do, so retroactively applying to other constellations to try to make them more sustainable or less impactful to the ground. And one of the best things that we can do for Curious is build it into our orbital design. So don't go into one of these heavily populated orbits. And in addition, at times when there's near dawn or dusk where you get the most reflection down to Earth, you can maneuver your satellites so they're knife edge and they're not reflecting as much light down into your ground-based telescopes. So a big focus of Curious is kind of building sustainability into the design as we're doing it so that we don't have to go back and fix it afterwards. And one more thing I'll say about Curious before switching into the high energy is that we're doing it in a few stages. So I've mentioned already that we want to launch 3 Curious CubeSats called Curious ID. We're actually launching the Curious Exploration demo, so Curious ED. The names are a little bit confusing. We're still workshopping the first one. This one will launch in February 2027, and this is just a scaled down version, so it's launching on a 12U bus. It's made from completely commercial components. So this is a Samara optic up here, and then we have a Xiphos CPU over here. These have all been flown before. They're sold as space-grade components. The biggest risk factor is this commercial camera that we've decided to launch back here. We've chosen to do this because it has a Sony IMX455 detector inside of it. That's a lot of numbers, but if you don't work with detectors, basically this is a new CMOS detector. It's really big and has really small pixels, so it's very useful for time domain astronomy. However, any space grade camera package that has it is incredibly expensive, so we opted to try to space qualify a commercial package ourselves. So nothing in the system was meant to go into space. And in the past couple of years, I spent putting it through its paces, putting it into thermal vacuum, doing vibration testing and radiation testing. And we're confident that we can send it into space and at least get some data out of it. We'll see how it actually behaves once it gets on orbit, but we're estimating anywhere from 6 months to a year with it. Okay, and then I'll end with showing this exciting picture that we took with Curiosity last week. This is the San Francisco skyline. We were taking these photos as a focusing test for Curiosity, but ended up getting something quite beautiful out of it. I have a couple photos in the backup slides if anyone's interested, but you can zoom in pretty far on this and actually see people on the side of the Salesforce building. Okay, so I do want to talk a little bit now about the short timescale side of the compact objects. And this is looking through the high energy lens. And so most of our high energy events come through kilonovae, supernovae, and the best way to view these is through large instantaneous sky coverage. So you really want to see all of the sky at once. They're incredibly short-lived. So if you're not looking at that patch of the sky, it's going to be gone most of the time before you can get to it. You want high cadences so you can look at these short events, and then you want to go deep as well. So I'm focusing on doing this through the Compton Spectrometer and Imager. For anyone unfamiliar, COSI is a funded NASA SMEX mission. It's being PI'd by John Tomsic at Space Sciences Laboratory, and it's slated to launch in August of 2027. This is what the Curious satellite looks like. It's about 5 feet tall. And then we have most of our payload up here, and then Northrop Grumman is building the spacecraft down here. COSI, I'm going to only say a couple things about it. It's going to be a very exciting mission. It's built around these very novel germanium cross-strip detectors. By using these cross-strip detectors, COSI can actually do gamma ray imaging, which is very exciting through a Compton imaging process. And it's going to be looking in the 200 keV to 5 MeV bandpass. So it's a very exciting experiment. I've got a QR code if you're interested in it at all here, which I encourage you to look into. However, I have not worked on this very much, so I'm going to switch gears to a different instrument on COSI. So there is a third detector system outside of the COSI main detectors and the shields on COSI. It's called the Background and Transient Observer. I functioned as the student PI for this mission over the past few years, and it's composed of 2 sodium iodide scintillators on either side of the COSI instrument. So you can think of BTO as similar to GBM on Fermi. So BTO is going to look at lower energies and provide spectra than COSI is capable of doing. So we're looking in almost the hard X-ray, 30 keV up to 2 MeV. We'll have an energy resolution of about 15 to 20% at 662 keV. We're actually seeing that we get better, closer to 10% through testing. So we're kind of crushing this requirement right now. our sky coverage per detector is going to be 60% of the sky, so we will see the entire sky at once with both of our detectors. And then we're going to do localization through kind of a strategic design choice. First is that we've placed the detectors on either side of the COSI instrument, and then we place them high enough that our field of view for each of the detectors completely overlaps COSI's field of view. COSI is going to do good localization, so anything that goes off in the shared field of view will be localized by COSI for us. Anything that goes off outside of COSI's field of view, thank you, we will do through detector shadowing. So the detectors are on either side of the COSI instrument. If a gamma ray burst goes off over here, we'll get more counts in one detector than the other one. So we can say it's either on the Earth, the sun, or it's actually a galactic event. And then COSI has, BTO has two different goals. First are the science goals. The first one's going to be monitoring transient events like gamma ray bursts and magnetar flares. And then the second is going to be improved background modeling in the soft gamma ray regime. Additionally, BTO is a student collaboration project, which means that we've trained many students through this mission. I'll highlight some of them here. So basically for BTO, any role that you would have on a normal mission has been led by a student. So we have our mechanical engineer over here. We have software and testing, software and comms. We have GSE and harnessing, as well as electronics and system testing. And then we have a bunch of fantastic mentors who have been very useful to me, as well as to all of these students, to make BTO a reality. And before I end talking about BTO, I do want to dive a little bit into what science we can do. So I've mentioned a couple times that we made BTO compatible with COSI, so we're looking at lower energies than COSI is capable of doing. We made sure that our field of views overlap, which means that anything that goes off in the shared field of view will have a broad spectral range for. So this down here, this plot down here is showing you a gamma ray burst spectrum simulated with megalib. The black line is showing you for COSI, and then the green is showing you for BTO. And what I really want to highlight here is what science we can do with BTO in addition to COSI. So these ranges down here specifically are good for photospheric emission, potential photospheric emission in gamma ray bursts, as well as constraining the energy peak turnover in gamma ray bursts. In addition to this, we've optimized BTO's bandpass to be capable of detecting magnetars flares, which peak in this regime right here. So through BTO, we'll be able to probe more compact objects, and specifically these transient signatures associated with them. And then I'll just quickly show here, we have some simulated plots which show how many GRBs we expect to detect per year. The gray is showing you how many simulated events would occur over 2 years. Orange is showing you how many long gamma ray bursts BTO would detect with greater than 5 sigma confidence. And then pink is showing you what we would get for short gamma ray bursts. So we'll get about 100 long gamma ray bursts per year and about 10 short gamma ray bursts per year. This is pretty typical. You expect something like 20 short gamma ray bursts or 20% short gamma ray bursts. So we're a little bit low there, but it has to do with the BTO geometry. And then finally, I'll show that BTO we've treated as a real NASA mission. We've gone through all of the paces, including our own design reviews. And this is our current timeline. So we're actually in April now. We'll deliver BTO in May, which means that we're doing our final flight integration and testing right now, which is very exciting and also a lot of work. We'll do a system level testing with all of the COSI payload over the summer, and then it launches in 2027. And this is a photo from our successful design review back in, I think, December last year. Perfect, and then I'll leave you with my 2 science takeaway plots. Over here we have our microlensing with Curious with 50 stellar mass black holes per year. And then over here is our gamma ray burst events with BTO. And I'm happy to take any questions.
Right, I'm pretty good on brand for what I've looked at. So from gravitational microlensing, either with Curious or with the astrometric follow-up, would it be possible to get any constraints on the environment of those black holes?
So I can't comment on that. I don't think anyone's thought about this application for Curious yet. I think the answer is yes. I just don't have any quantities for you. I think it's a good idea.
Is exciting.
It is super exciting. Yes, I think one of the things I usually do when I give one of these talks is we're actively looking for science collaborators on the mission. So if you want to talk more about what requirements you would need to be able to do this, I'd be very happy to do so. Yeah, thank you.
Other questions?
Simple question about the optical instrument. It sounded like to get to the depths to the magnitude limits that you want to, it's gonna be static.
Yes.
So, and a fair amount of it, I don't know how many images you use that, but that, if you really end up still having good signal to noise, that means the read noise has to be really low, is that right?
Yeah, so I'll add a couple things. Read noise is low. So with these new Sony CMOS detectors, read noise used to be a limitation for read noise because you have so many different pixels reading out at the same time. Sony's really pushed this envelope. So in the gain mode that we're in, we get 3 electrons for our readout noise, which is completely doable. You can push it down to 1. I'll also note that one of the reasons we're stacking on board is because of data volume. So each of these images for a very large format detector are 122 megabytes if you're using this specific detector. You can't downlink all of this data raw if you're doing 30-second cadences or 30-second exposures. And so we partially stack on board to reduce how much data we're downlinking to the ground. You can give up some of your coverage. So if you want to pause observing throughout the day, you can downlink shorter cadences and still have the same data volume, but there's a big limitation there for your data volume.
Okay, thanks.
Yeah.
About the stellar mass black hole microranging experiment, you mentioned that you expect about 50 from the galactic center. So I guess for that science, you don't need to cover full sky all the time. How many do you need it? I guess it depends on your orbit choice, right? In order to monitor the galactic center. How do you define actually galactic center in this context?
Yeah, thank you, Jason, for opening up the second regime of curious science. So on the stellar mass black hole side of things, with a 35-degree squared field of view, I think it's about 4 that we would get high rates of stellar mass 4 field of views on the galactic center that we would get high rates of stellar mass black hole microlensing. The idea is that we would do the entire galactic plane as well, and just kind of map what the rates of the stellar mass black holes are in the galactic center versus outside of the galactic center and the galactic plane. What really pushes for all sky coverage is the explosive science case, which in this talk I focused from the high energy, but Curious will also be very good for detecting optical signatures to supernovae, kilonovae, things like that. And so that's what's really pushing us to look at the entire sky all of the time. Yeah, thank you.
I have a quick question. Do you guys plan to follow up with any specific detection for ENM counterparts or remnants of LIGO sources?
Yes, yeah. So for Curious, there will be a TOO capability. It's about 6 hours that we can get information from the ground up to a CubeSat to get it to look somewhere. But yes, we fully intend on following up to LIGO events. Yeah.
Excellent. I have one quick question. Maybe this is obvious, but what plans does Curious have for mapping, if this is relevant at all, maybe second pulsars in the galactic center and quasars? You have mentioned magnetars, but.
Yeah, so I think this is another science case for Curious that hasn't been explored in depth. We'll definitely detect them because we'll be looking at those regions on the sky. But they are a bit fast for current cadence for Curious. So it might be a tweaking of the design parameters that we currently have. Yeah. Yeah, thank you.
Is there any questions on the? Okay, great. If there's no further question, let's thank both speakers. Yeah, see you next week. See you next week. Guys.
Yes, yep.